First of all, regarding the final test, okay? The final test will be in 2 weeks on Thursday, January 30. Okay?
Can we discuss it? Because the semester ends 2 days.
Yes, that's right.
So we won't have time.
But that's essentially fine because you know it's you don't need that much to prepare because this is not an exam. It's really a homework. So you take everything to home and you have every material opened. Otherwise, we are in the troubles. So if you go to a different day, it will always overlap with something else. So
on the day that's
what day do you find?
the 22 of February.
22 of February. Somebody was complaining about that.
22 of February, it's Saturday.
Saturday is not a good day, so I can give you for Saturday if you wish to work that day. Usually, not all people can do that. So let's respect Saturday. Yeah, but you know, again, so it's essentially not something that you really. So you get everything to have, you know, everything open. So it's completely open material. So if you did everything, I mean, you will never get more than 2 days to prepare, whatever day we choose. Otherwise, you know, another opportunity or another option is to move it to somewhere close to Pesach, where you get Moed Bet. So the second chance to make. That's the only opportunity. So in February there will be no other day possible. So I didn't find from the material that I got.
Sorry, could you repeat the point? You said the third. You said
so the semester ends on Sunday, Monday, Thursday, Sunday, Monday, Tuesday, right? I think
It's the last day in the
Tuesday.
classes. Yeah.
Sunday, Monday, Tuesday it ends, and so essentially there are no exams scheduled for 2 next days. Wednesday and Thursday are sort of free from regular exams. I suggest to use this 2 days to have a final test on atomic physics for one of them, whatever you wish.
Sorry, I told you because I heard that you said February 3rd.
No. I'm talking about the end of January.
Okay, for me everything is okay. For me, the end of January is okay.
So it was, I suggested January 30, which is,
Okay, 29.
if you wish, 29, it doesn't matter for me. So whatever you wish.
I think we have to do
29 is
because
better.
a week after that we have quantum mechanics.
So physics
For lasers.
For lasers also.
Yeah.
Lasers are not that far from what I'm doing here.
29.
Actually, the natural preparation to the exam.
We don't need to prepare that much.
אני נראה שמע לפי 29, למרות שאז יש לנו אפס ימים להתכונן כביכול.
יש לך חומר פתוח, בסוף כאילו זה מבחן שיש לך יום שלם לעשות.
Yeah, right. So it's you know it's not like a regular exam that you really need to remember many things. So if you did your homeworks and you followed me and you know used half a day in a week to follow what we're doing here, that should be okay for you to spend 24 hours doing this exam and forget about that. So that's the only option we can do. Right, so we decided on 29? Good. Okay. So 29 of January, I will release this test on the web page at 9 o'clock in the morning. Those of you who want to come to collect the paper from me, so you can do that. Though I am not do not promise that I will be here. But it will be uploaded to the web page of the quiz at 9 o'clock, and I expect you to return me, this is now, next day at 9 o'clock. You can return whenever you want that. That's the deadline. Okay. So you can return me 1 hour after the 9 o'clock of the same day, then not later than 9 o'clock the next day. Okay?
How do we submit it?
So, whatever you wish. So you can bring it to me physically. You can put it in my box here. You can send it by email. You can do any digital submission, whatever you want. At 9 o'clock, I take everything that I have in the box and I stop accepting. So what does this mean? This means that if you still need some time to talk to me, that it usually costs you some points. Okay, the submission after the deadline. Well, if nobody submits until the deadline, then probably I will not reduce the points. But let's go like that. That this should not be the case, okay? So this should not be the case. So we discussed today with Rui something that was a bit in advance. That this is the last time that he is coming to talk to you. So next time, next week, the lecture starts at 10. There will be nothing at 9. Okay, no one will be here at 9. I will be here at 10, so that will be the last lecture of the course. And it will be as a usual lecture. Fine. Okay, so we talked about optical Bloch equations that solves the problem of two-level system. So I remind you several steps that we did last time. So we consider two-level system. So we only consider two energy levels of an atom. And this two-level system is submitted to electromagnetic radiation that couples these two levels. And this is a monochromatic light with a single frequency, and this frequency is considered to be close to the resonance. So this is the system that we solved. So we solved this system considering matrix, density matrix of the system. So in order to take into account a statistical mixture of possible states. It's not a pure state. It's a density matrix that considers all information that can include also the decoherence of the system due to different sources of decoherence. One of the sources we will consider today. So we will clarify these different sources of decoherence. But before doing that, we actually considered the solution of this density matrix, the time development of the density matrix without any decay processes. So we essentially considered the development in time under the Hamiltonian, where in the Hamiltonian we had only the kinetic energy and the interaction between this two-level system and light without any decay. So and we considered this time evolution of the density matrix under two main assumptions. The first assumption was rotating wave approximation, and the second assumption is the rotating frame that we consider this system. So we were able to reduce this density matrix, which is 2 by 2, so it's 4 different elements. These 4 different elements we wrote as 4 different differential equations, which are coupled, of course. But these 4 different elements are not completely independent. So we have some additional requirement, which is considered the preservation, right, so, of the material. So the atom cannot go disappear somehow from the spot. So we should have the sum of diagonal elements of this matrix to be equal to 1. So this actually reduces 4 equations to 3, so 3 independent variables. And these 3 independent variables, we made several, under the action of these 2 assumptions, we were able to reduce to a matrix which is time independent. And we essentially were able to reduce this equation to a simple vector equation where we have torque and the vector of V in the 3-dimensional vector with projections on axis U, V, V, W, and we gave an interpretation of this new elements of V, U, V, W. W, we gave the interpretation of difference between the population of the excited and ground state, and U, V, V, there are actually 2 different elements of a dipole of the atom. So one of this dipole element is in phase with the external electric field, and the second one is in quadrature. So one has the cosine modulation in time, and the second one has the sine, sinusoidal modulation of time. So that was essentially the result that we saw last week. I want to spend the beginning of this lecture giving some more insight into this interpretation. So we actually want to make some geometrical interpretation of this interaction. For that, we are going to map this problem to a 1/2 spin. So spin of 1/2, which is submitted to the magnetic field modulation. So some magnetic field which is modulated in time. So we want to map the problem of 2-level system in electromagnetic submitted to the electromagnetic radiation to some to a problem of spin 1/2 in a magnetic field. So spin 1/2, we know that is well described by Pauli matrices. Okay. And this is what we want to do. We actually want to introduce this problem under the action of Pauli matrices. So the general subject is optical Bloch equations, and so the geometrical interpretation of them. this will give you the idea of these assumptions that we did a week ago. Okay, so now let's make this mapping. So mapping to spin 1/2 problem. So how to do that? So we consider the state A as a state minus, okay, of the spin that is in the direction down, and we have the state B, which is plus. Okay, so there are two different directions of the spin. One is up, one is down. So now we have this possibility to describe the operator Px. So we describe the operator Px like an operator of diagonal operator, which corresponds to a sigma x operator of Pauli matrix. But we add 1/2 in order to make a suitable mapping. Now we describe the operator Py, which is equal to 1/2 of 0 minus I 0. And then we have Pz, which is equal to 1/2 and 1 minus 1, 0, 0. So these are essentially Pauli matrices, right? Sigma x, sigma y, sigma z, but up to a factor of 1/2, right? So 1/2 is the only additional factor here. So if we have these operators, now we can take the Hamiltonian of atom. So Hamiltonian of atom, if you remember, was in our previous language, the atomic Hamiltonian was just h bar omega 0 BB, where B is the excited level, right? So this is the excited state of the atom. So the zero energy was at the ground state. So now if the atomic Hamiltonian, what we want to do is just to describe it in this way. Oh, we can describe it as we need the on-diagonal element here. So on-diagonal elements, we have 1 minus 1. So in order to do that, to make the mapping, we can describe it like h bar omega 0 divided by 2, multiplied by unitary matrix with 1, 1, on-diagonal elements, and minus, plus Pz, matrix Pz, which is multiplied by h bar omega 0. So if you do this representation of the atomic Hamiltonian, we get exactly the atomic Hamiltonian that we had before. So, but now this Hamiltonian is represented in the language of Pauli matrices. So the other part of the Hamiltonian is the interaction Hamiltonian. So the interaction Hamiltonian is electric dipole Hamiltonian. So this electric dipole Hamiltonian is essentially can be represented by Px matrix because it's truly off diagonal Hamiltonian. So electromagnetic interaction between the two-level atom and electromagnetic field can be represented simply by 2 h bar omega omega Rabi. So that's the Rabi frequency that that makes this stuff. So here in the Rabi frequency, you have this matrix element of the dipole operator multiplied by the strengths of the electric field divided by h bar. So this is why h bar is here. So now we have only the cosinus of omega laser multiplied by t. So that's the modulation part. And here we just multiply it by the px operator px, right? So this is the mapping. So how we map the problem to the problem of 1/2 spin in the magnetic field. So now we can draw it here in the x, y, z coordinates. X, y, z coordinate. So x, y, z coordinate. Here in this Hamiltonian, we have these Pauli matrices. This means that we have essentially the magnetic field that goes in the direction of z-axis, right? So I will draw that like that. So this is the BZ, right? That's the magnetic field. Or we can just describe it like a B0 because this magnetic field has the value of omega 0, right? So so we have the system so that makes the precession around this magnetic field in the z direction, and this precession is this Larmor frequency of this precession is equal to omega 0. If we were submitted only to the Hamiltonian, which is the atomic Hamiltonian. So just in the presence of the atomic Hamiltonian, this means that we have only magnetic field along z-axis, and the value of this magnetic field is equal to omega 0. Okay, so now if we have optical excitation of the system, which is time dependent, so here we have actually the magnetic field, which now directed along x-axis. Okay, so in this magnetic field, can be written like that. So this is the direction of the magnetic field, and they are really different in values, right? So this one is very, very large. This one is very small because the omega 0 is usually significantly larger than the Rabi frequency. So here we have this value of 2b1 multiplied by cosine omega. So I will write it a bit down in order to then. So it's here 2b1 multiplied by cosine omega laser multiplied by t. So this is the cosinusoidal modulation, right? So this magnetic field is actually modulated. So it goes in this direction, back, forth, right? Minus 6 plus 6, minus 6 plus 6. So what we do in order to make some geometrical interpretation of our approximations, we do the following. So we decompose this cosine function into two phases, right? So one would be equal to b1 multiplied by e to the power of I omega laser t plus e to the power minus I omega laser t, right? So this is what we have as a representation. So one rotates clockwise, the second one rotates counterclockwise, right? So these are two vectors. So now one rotates clockwise, right? And the second one rotates counterclockwise. Okay, so now the system that we have here, first of all, is this spin 1/2 is rotated clockwise around B0 with the frequency, Larmor frequency, which is equal to omega 0. That's what our problem describes us. So we have a magnetic field along z-axis. We have our spin, right, which is directed along mainly along z-axis, and this spin rotates around the z-axis with the frequency which is equal to omega 0. Now in addition we submit this spin 1/2 under the magnetic field, which is in xy plane, right? So it's essentially in x direction, makes the modulation, but now we represent it by two different fields that rotates exactly the same frequency, but in opposite directions. One is clockwise and the second is counterclockwise. Okay? So essentially it's clear that if you take these two vectors and sum them up, you will get only cosinus modulation along the x-axis. So, but now this is a clear picture in order to understand all our approximations. So first approximation that we did was rotating wave approximation. So what does this mean, rotating wave approximation, in this representation? So it means that now look what's going on with these two values. So this vector rotates at the frequency of omega laser clockwise, and it actually follows very closely the rotation of the system clockwise around the B0. So remember that omega laser and omega 0 are close to each other, right? So the omega laser is very close to omega 0. Or to omega 0, which is the frequency, the difference between the ground state and the excited state of two-level system. So therefore, this vector rotates and nearly follows the fast dynamics of the system around the z-axis. Okay, so the system goes around z-axis, precess, and this vector precess in the same direction. So they are really nearly, so the difference between them is really small. Okay. This term, in contrast, rotates in the opposite direction. Okay. So it makes the counterclockwise rotation. And this counterclockwise rotation is as fast as clockwise rotation of the system around the z-axis. So this means that the change, right, that this system sees is as fast as nearly twice the frequency of, whatever frequency you choose, because they are close to each other. So whatever time you will consider in this system, or whatever phase that you would like to consider, you will very fast realize, you can really see that this phase is not important. So whatever you can average on time. So whatever happens in comparison between this field and this rotation, it's much slower, right? So they really nearly follow each other as compared to what is done by this field. So this field makes a lot of rotations, while these two fields nearly follow each other. So this will just average to 0. This phase will be averaged to 0. So this is the rotating frame approximation. So the rotating frame approximation, rotating wave approximation, sorry. Rotating wave approximation means that we want to neglect completely the counter-rotating term. That's the idea of that's geometrical interpretation of the rotating wave approximation. Let's drop completely this counter-rotating term. It's not interesting for us anymore. So dropping this counter-rotating frame, we can represent this problem by the following. So now we have Z, X, and Y. So the only term that are that we consider is the term. So it's the term that makes the same rotation. So if it's clockwise rotation, so this is the clockwise rotation of the story. So now we want to make the following. So we are taking this guy and we actually make the rotating frame. So which means that we actually take our system and start to rotate the system exactly at the same frequency as omega laser. So this means that we actually rotate the system. The system starts to rotate around Z axis. This is X prime, Y prime, and this is omega laser T. This angle of rotation is omega laser T. Okay? So this means that when we do that, right, so we essentially rotate together with this, and this is rotating frame. Now this is rotating frame. This we did when we exchanged the variables. The last exchange of the variables was the not the last one, but the first exchange. After the rotating wave approximation, we did the rotating frame, so we exchanged our variables with the variables multiplied by this value. So, and this is essentially the rotating frame. So rotating frame is just to sit together with this rotating magnetic field that makes the rotation. So if this is what we do, then we can actually say that the magnetic field B0 is no more as strong as that, because they are nearly, they are very near this action of this omega laser and the action of B0. So we can say that the magnetic field that we have now, the B0 is now becomes a small one, B0, which is essentially, due to the difference between omega 0 minus omega laser. So instead of considering omega 0 and omega laser, we actually consider a single variable, which is the detuning, which we call the detuning, right? So this is actually what is the difference between omega laser and omega 0. So that's the magnetic field, and this magnetic field is significantly smaller, right, than this. And in the rotating frame, when we're sitting in the rotating frame, then the magnetic field here, B1, is essentially equal to omega Rabi. So this is the second magnetic field. So now we see that our system is submitted to a magnetic field, which is the sum of two magnetic fields, and these two magnetic fields are comparable in the value, in their size, right? So this B0 and omega Rabi, they are of the same order of magnitude, and they are the finite magnetic field that the system fills is essentially the sum of both of them. So the system precesses around this
magnetic field, which is essentially the value of effective Rabi frequency, which is the sum of the Rabi frequency squared plus this delta squared. So this is essentially the result that we obtained considering the two-level system. This two-level system, or the vector block, persists around the driving field, and this driving field is now is defined by the sum of two fictitious magnetic fields, right? So this fictitious magnetic field and this one. So this one is the Rabi frequency essentially, and this one is the tuning. That represents the tuning. Okay. So I think that this picture, this geometrical picture, is really clear. To understand what are the the game changers in this game. Who defined what? Right, so you see that the rotating frame, the rotating wave approximation is just we drop off the counter-rotating terms from the story. So and then we see it in the rotating wave frame, the rotating frame, in order to reduce the time dependence of matrix. And now we can just consider this, all these magnetic fields become time independent. The system processes around this final magnetic field, which is defined by the Rabi frequency and the detuning. So now we can see how this system oriented. So if so if we have zero external fields, so then we have vector block which is projected to -1 axis, and then we can apply some driving field. This application of the driving field means that we switch on this effective Rabi frequency, and then switching on the effective Rabi frequency, the two-level system starts to oscillate around this driving field. And then, depending on what you do with the driving field, you actually can orient your system in any direction on the block sphere. That's the language, okay? So, remember that we did this exchange of values. So we have this UVBW. So now our block sphere is just the three-dimensional unitary block sphere with unitary radius. So the position of, the two-level system described fully under the interaction of external electromagnetic field is fully described by the language of block sphere. So the point, when you just define the point on the block sphere, so you can define anything, everything regarding the two-level system without the decay yet. So then we can say that we can write actually the complete solution of the system. So remember that there are two different situations that we can have. So from here on, I can So I just remind you that we had these three different vector with three-dimensional vector that we defined as u, v, v, w. So w, I remind you that this is what we did. So we defined it as sigma BB tilde minus sigma AA tilde. U, we define it like 1/2 of sigma AB tilde plus sigma BA tilde. And V, we define it like half of I sigma AB minus sigma BA. So in this situation, we will come back to this definition because in this situation it's more convenient to work at when we add decay, especially in two-level system. But currently, without the decay, so the additional language, and I told you that additional possibility is to define these two values. Actually, and this is the language of block sphere, actually more known, that this 1/2 does not exist. So instead of making that with 1/2, this is the definition that we can do. So in this situation, we have the block sphere with the value of u squared of t plus v squared of t plus omega squared of t is equal to 1. So this is the unitary sphere. So in this situation, without 1/2. And then we have this language of the block sphere, and we have the optical block equation can be described by a single vector equation of rho. Vector rho developed in time as a function of time is equal to omega, the matrix cross vector rho, and this rho is just the three-dimensional vector with the coordinates u, v, w, and omega is the vector which is defined by omega Rabi 0 and minus delta. So if I'm doing that, so then this this equation, optical block equation, can be actually represented by the development of vector block as a function of time with a matrix 3 by 3, which is equal to 0, delta, 0, minus delta, 0, minus Rabi frequency, 0, Rabi frequency, and 0. And this is multiplied by vector rho. So now, if you do that, so you can have the analytical solution. This is the Rabi solution. Analytical solution of this equation can be done. And this solution okay, analytical solution to this problem is the vector u, v, w is equal to, so I'm writing you the this complex matrix that describes the analytical solution. So it's Rabi frequency squared plus delta squared multiplied by cosine effective Rabi frequency multiplied by t divided by effective Rabi frequency squared. here the second element is delta divided by effective Rabi frequency multiplied by sine omega t. And the third element is minus delta Rabi frequency, effective Rabi frequency squared, 1 minus cosine omega t. That's the first line of this matrix. And the second line of this matrix is delta divided by Rabi frequency. So it's symmetric as compared to this element. Sine omega effective t. Then we have here cosine omega t. And here we have the Rabi frequency divided by omega multiplied by sine omega t. And the third line in this story is minus delta, what we have here, minus delta Rabi frequency divided by omega squared multiplied by 1 minus cosinus of omega t. And here we have minus omega Rabi divided by omega multiplied by sine omega t. And here we have delta squared plus omega Rabi squared divided by multiplied by cosine omega t divided by omega squared. So this is multiplied by the initial condition of u0, v0, and w0. So essentially, it's time development. This is the solution. This is not the equation. This is already the solution of this equation. So this is known as a Rabi solution. So I'm just wrote this solution. You can find them in the book of Ilan and Eberle. So this is Ilan and Eberle, book, chapter 3.3. So Ilan and Eberle, this is the book of a two-level system, and I forgot exactly the name of this book. It's something like two-level system, and in their electromagnetic field, so it's something like a two-level system. So this is the solution. It's analytical still, but now you can actually apply anything that you want with this solution and get the time development of the block vector. So this is still simple situation. So I just remind you that this situation do not have any decay. So in this story we have only this is of course the omega is equal to square root of Rabi frequency squared plus delta squared, right? And delta is omega laser minus omega atom, or omega 0. That's the language of this equation, or this solution. So here we have initial conditions, right? So, and this is sort of the analytical solution of this equation for the development of time. A general one, right? So depending on what is the initial conditions, right? Ilan and Eberle, that's the authors, okay? Ilan and Eberle. So it's a well-known book from 60s, if I remember correctly. So if I don't remember, I will have a look at the name of this book at the break, and I will give you the name. So it's a really classics. It's a small book. and the classical one that cost, I think, $8 on the Amazon. So it's published in this Dover Classics, so it's really cheap. Of course, in the laboratory you can see, in the library you can find this book. So this solution gives you some interesting insight. You can see it if you just have a look at what's going on. Now what we can see in this story is that you can. It's a bit difficult to understand what's going on, but if you start from something which is it describes everything essentially. So, for example, it describes the work of principles of some basic ideas that we have, and part of the homework that you have on the web page, the last one, the fifth one, is essentially to play with the block vector and see how it's developed in time, and compare the Rabi pulse and the Ramsey pulse, or Ramsey sequences, in order to understand how the atomic clock works. So this is the basics. Not only about, so we are talking not only about the quantum qubit, so quantum qubit described by the system, but this is just the basis of that. But here we can talk about the application of the story to clocks. This is how the atomic clock works. So the atomic clock works exactly on this basis. So that was the idea of Rabi, how to make the precision measurement of the transition between two energy levels of the spin 1/2. So that was the idea that Rabi worked on. So Rabi worked on spin 1/2 in the magnetic field, and he tried to measure, to make the precision spectroscopy between the two different energy levels of this spin 1/2 system. And his idea was to apply time variation of this magnetic field in order to measure the precision in precise way, the resonance between these two levels. So, and the idea was that we can make the Rabi pulse, the pi pulse, right? So that's the Rabi solution, to make the pi pulse. And this pi pulse will bring the system from ground state to excited state, right? If it's the exactly, so we wrote that, represented that already as a function of time. So that's the excited level as a function of time squared. So the population of the excited state is a function of time. So if it's 1, right, so this excitation looked like that, right? So it's just modulated in time. If the detuning is equal to 0, for delta is equal to 0, so we can factor the pulse. This is the Rabi frequency multiplied by time. This is the pi pulse. This is 2 pi. This is pi. So at time pi, so after Rabi frequency multiplied by time equal to pi, this is why it's called pi pulse, to actually bring the population totally in the excited state. So on the language of Bloch sphere, we also describe that like, if you have the population W goes in the initial to the -1, right? So now you direct your excitation field along the U axis. Now your vector, Bloch vector, right, we did that that way. So the excitation was in this direction, right? So the U. So the Bloch vector did this. So from the -1 goes to 1, right? So this is the representation at detuning equal to 0, what Bloch vector does. So exactly after pi pulse, you excite everything to the excited state. So, but now this happens only if the detuning is equal to 0. right? So, and this is described by this equation. So initial condition is equal to 0, 0, minus 1. So initial condition at time equal to 0. All population sits on the ground state. So the W is equal to minus 1. And then you apply your time. So in time, you start to develop it under the condition of delta equal to 0, for example. So delta equal to 0 simplifies a lot this equation, right? So here is 0, here is 0, 0, 0. Many zeros appear here, so the matrix becomes simpler. So you apply the development of this matrix at essentially after time, which is equal to Rabi frequency. So pi divided by Rabi frequency. After this time, you will get all the population up, right? So now you can measure where your population is. So now you can measure where your population is as a function of frequency. So you measure where the population. So for example, you measure the excited level population squared. So the population of the excited state as a function of delta of the detuning, right? So now what do you get? And you keep your time of the pulse, of the excitation pulse, always the same. Okay, so what you get? You get some function which is peaked, right? If the tuning is equal to 0, then you get here 1. Right? This is what we understood. But if you miss the resonance, then this excitation will give you something smaller than 1. And it gets and actually drops down. Okay, so it's a sinc function essentially. That you can understand why it's sinc function, because essentially this is the Fourier transform of your time pulse. This is the frequency domain, right? And in time domain, you essentially excite your system by a single pulse with the duration of this pulse as t1 is equals, this is t equal to 0, t0 equal to 0, t1 is equal to pi divided by Rabi frequency. That's the time. So that's the time that you excite your system. So and here you get actually the Fourier transform of this pulse, and that's you get the same function. So this means that you can define exactly right the resonance between these two systems. So you don't know where it is, right? So you just define some time. So you look for the resonance. So you look for the maximum of the excitation. So you understand that at this position you can define this resonance condition between the two levels. So and what is the precision that you can define this? So essentially, you know what atomic clock is. So atomic clocks is just you have to measure precisely the difference between the two energy levels. So once measuring precisely the transition between two energy levels, so the energy is just 1 over time, and you define time in this manner. So, but you need to measure them precisely, okay? So, and precision of this measurement is defined by the width of this peak, right? So that's the more or less the precision that we can define this transition. So this precision goes like a 1 over t, which is t is exactly this duration of the pulse, right? T1 minus T0, or equal to pi over Rabi frequency. So that's the precision, that you can define the position of the resonance. So in order to increase the precision of this measurement, right, you really want to increase this time as much as possible, because increasing this time will just shrink the width of this resonance, right? That's the idea. Well, but there is a price to pay, right? So if you want to increase this time as much as possible, you need to increase the interaction range. the region of interaction should be increased. So, right? So this is the region of interaction. So in order to keep this equal to pi paths, of course, you just decrease the, the strength of the interaction decrease, and then you can increase the time. So essentially, to keeping the area equal, so you can decrease the strength and increase the time. That's the optimal thing to do in order to improve the resolution. The point is that you have to increase the interaction region. So how this interaction region is defined? So it's defined by the time that you have to interact with atoms. So usually atoms fly very fast, right? So that was the time when Rabi invented his technique. So that was the only atoms that were available were thermic atoms. So they fly with large velocity. So you can have the atoms starting from a certain oven that goes through the region of interaction, so and they go through the range of the interaction very fast because they have hundreds of meters of seconds velocity. So then you have the interaction time, which is limited by the size of your apparatus. So if you take your apparatus larger and larger and larger, that will limit the size of the interaction. So, but this is the magnetic field, right? So I remind you, so you have to keep your magnetic field very uniform on the size of your apparatus. So that was the limitation, essentially. The limitation was how good you can build the magnetic field in such a way that it will be uniform over the whole size of the apparatus. So that was the limit. The limit was about 1 millisecond. That more or less what you have. On a meter, let's say this is what you more or less can make the uniform magnet. So it's not especially the problem of the uniform magnet. It's especially very difficult to make the uniform environment, right? So uniform magnet and uniform environment is really important for all this story. Okay, so that was the idea of Rabi, and then and he got Nobel Prize on that. This is also a main tool that people use in nuclear magnetic resonance. Well, essentially the main tool that people use is the student of that was invented by the student of Rabi, whose name is Ramsey, who got Nobel Prize for his invention. So his invitation was actually, he realized that this is not what you exactly need. So you don't need a very large magnet in order to make a correct measurement. You can do it differently. So, and this can be understood also on Rabi. On the language of block sphere. So what we do? So the Rabi's idea was to take the block vector and to bring it completely to the excited state and then to measure, right? So for that you need really a pi pass in order to do that. What Ramsey understood was that you don't need to do that. So you can actually do something different. So you can excite. Instead of doing this pi excitation, so you can excite your system into superposition state of ground and excited state. So you take the driver, right? So you make it strong, and then you just excite your system instead of directly into the excited state. You actually excite it into the UV plane. So you bring it in the UV plane, and then you leave it. Okay, so you leave it on the UV plane, so you switch off the interaction, and then you just wait for as much time as possible, and then you bring the second pulse. So that was the Ramsey interferometer, which is based on 2 pi over 2 pulses. So the pi over 2 pulse is this one, so the one that brings the system in the superposition state. So this is pi over 2. That's the time pi over 2. So I expect to have here at this situation 1/2 of the population of the excited state, 1/2 of the population of the ground state, but this is the coherent superposition. So the wave function is essentially square root of 2 of being on A state plus B, right? So this coherent superposition state is develops in time, right? So this A and B, they have different different frequencies, so it develops in time. And if you can see it actually on this graph, right? So what's going on? So on this matrix. So if I make the pi over 2 pi, so this is what I get. So I get some excitation. So and then what I will have. So and then I switch off everything. So switching off everything means that I'm getting a radio frequency which is proportional to the E to the excited state. Which is proportional to the amplitude of the electric field. It will be 0. But does this mean that all matrices will be 0? It's not, actually. This matrix will not be 0 at any position. So it will be, look at this, right? So everywhere that you have the Rabi frequency, it will be 0. So this is 0. This is 0. This will be equal to 1, right? Because this is 0. This one is square root of Rabi frequency plus delta squared, right? Then this is squared, so delta squared divided by delta squared give you 1. So this is 0. So this is 0. This is, but now it starts to be interesting, right? Now it starts to be interesting. Look what you have here. So here you have but here you have delta square. Delta square is 1, and here you have cosine delta. So here you have the Rabi frequency, which is 0. So I have here, I'm writing you the matrix. So here you have cosine delta. Cosine delta t, right? So here what do you have? You have here a minus sine delta t, right, in this story. So now here you have 0. So and then here you have also sine delta t, and here you have cosine delta t. So here you have 0, here you have 1, here you 0, 0. This is your matrix. So under this matrix, there is a time development. So remember, no excitation field. The excitation field is switched off. It doesn't exist. But the matrix is not 0. It's actually a rotation matrix in UV plane. Right, so it's UV plane. So the system rotates in UV plane. So the dipole that we excited, so right, this was where we excited the dipole. So once we excite the dipole do not go anywhere, so it continues to develop in time in UV plane. So how it develops in time? It's a rotational matrix around in the UV plane. So the vector rotates in UV plane depending on what detuning that we have. So if detuning is equal to 0, right, then the vector, the block vector just arrives in the UV plane. So the projection on the UV plane is, so it's 1 along V axis. So this is U, this is V. And then it stays, because if it's 0, then this matrix is 1, 1, 0, 0. So it's diagonal matrix, nothing happens, so it's not rotate anymore. So it's wait in this position. So it waits for this position for any time that you have. And then once you come again with pi over 2 pulse, you bring your vector, you continue to develop the same technique, the same continuation that you have in the beginning. So the vector just continues to go up, and it arrives at the excitation, at the maximal excitation, where the population is equal to 1. So you essentially continue this up to the pi pulse. So essentially, to take 2 pi over 2 pulses very far from each other, if everything is ideal and the detuning is equal to 0, so it's equivalent to make a single pi pulse, right? So what do we gain in this story? So, but something does happen in this story. So it's a Ramsey technique, right? So it's a Ramsey techniques means that if we continue right now to see something which is not equal to 0, so if the tuning is not equal to 0, so that starts to be interesting. So you bring your vector to not exactly into the UV plane, right? Because your drive is not exactly in the direction of v, in the direction of u. It's a bit so depending on the vector, depending on the detuning, so it's a bit off or on, so above or below the UV plane. But your vector starts to precess, so you do not get exactly the vector at the UV plane, but it's somewhere close to the UV plane. And then this is what we need to have as a development of the vector. So this vector, after the pi over 2 pi, starts to rotate, right? So whatever direction, so in correct direction. So it starts to rotate. Whoop. For the tuning, by the way, it's dependent on the sign of the tuning, in what direction you will get. So with the positive direction, you go, with the positive detuning, you go in one direction, negative direction, and the negative detuning go in the opposite direction. Well, you start to rotate in this UV plane. So and then now this is the interesting question. So if you rotate exactly 180 degrees, right? So the vector rotates 180 degrees, it arrives here. So now I come with the second pi over 2 pulse. What happens? You go down. You project it back to the ground state, right? So that's what you understand immediately from the picture of a block vector. So it's described by this matrix, but you can understand that by considering the time development of the block vector. So it goes up. Now you wait some time. So you go, if you wait enough time, that will be projected back completely. If you wait somewhere in the middle, it will be partially projected up, partially projected down. And now if you wait time which is equal exactly the full rotation, so it's rotated and returns back, you get it again back to the excited state. So now it's really dependent on the time, right? So essentially, it can be easily understood that this pi over 2 sequence time, this is the Ramsey sequence. This is the Ramsey sequence. That's time, in time. So here we have two different times involved in the story. So one time is this one, right? So which is so you know, let's call it t small. And oops. This small time. So this small time brings us from, so it's a pi over 2. So this time is equal to pi divided by 2 times Rabi frequency, right? So that's the time. So the pi over 2 over 1 over Rabi frequency. That's the pi over 2 pi over 2 pi over 2 pi. Sorry. And now you wait some time, which is t, and then you come back with the same excitation, which has the same duration. So essentially, you know, it works more or less the same as the Rabi technique, but this is the Rabi suggestion of pi-pass, and this is the Ramsey suggestion. So, but what is the difference? The difference is that here you have to, you know, so either you make the full analysis of this matrix, which is possible, or you can understand, in analogy of what we have here, this sequence gives you sort of, in the frequency domain, it's a Fourier transform of these two pulses in time. So if you make a Fourier transform of this sequence, so in the frequency domain, it will look like that. There are two dynamics here, right? So that's the as a function. So this is this population on the excited state as a function of the tuning. So it's really different as compared to Rabi picture, right? So Ramsey picture is really different. But you can see immediately that the relevant, if you want to measure precisely the transition between the two energy levels, the precision, what is interesting for you is the width of this peak. So there are two different time scales here, or the frequency scales here, which are related to two different time scales in the story. So this is short time, long time, and here is a narrow frequency and broad frequency, which describes the general behavior of all this story in frequency. So this width goes like 1 over t, right? Because this is the short time. So this story goes like proportional to 1 over t, the long time. So long time defines your essentially resolution of a frequency that you want to measure. So and this resolution is defined by this time. But this time is essentially non-interacting time. That's the largest difference between the Rabi technique and the Ramsey technique. So Rabi said that I want your interaction range as long as possible. Ramsey say, I want your non-interacting region to be as long as possible. Right? That's the very big difference between these two techniques. So you don't need to build large uniform magnet. Instead, you need to build two small magnets in the beginning and at the end of the trajectory, and then you have to build a good magnetic shielding where the atoms will propagate, right? So you want to keep your non-interacting region isolated from all possible noises that exist in the story. But you have, it's easier to isolate your story, to make the zero magnetic field, to keep zero, to isolate everything from the environment, than to build large uniform magnets. So that's the difference between these two techniques. And the main, this technique is very well known. So all atomic clocks are working essentially on this Ramsey technique. So we will play with this in the homework. You will compare them, the Rabi and Ramsey. So you will be able to see yourself how it looks like, right? But any atomic clocks that we have in the story in the world, they work on Ramsey idea. So Ramsey technique works there. So it can be also the the hot atom clock, which is usually sits in many different elements that are used, the atomic clock, for example, GPS used the atomic clock. So this atomic clock sits in many different areas on Earth and on satellites. So we need to compare the time very precisely. So the way how to do that is this, to measure atomic transition very precisely. So this is how it happens. So, but nowadays people actually use already cold atoms, so that the temperature is reduced very much, so the velocity is very much reduced, so you can increase significantly the precision of your measurements. So the standard technique is now that the cold atoms are the part of the system that measures time. So the time is measured now in many different research institutes in the world. So it's this is the main purpose of the existence of National Institute of Standards and Technology. So it's NIST in the United States and different names in Europe. So in France it's LPTF. So it's the laboratory that measures time and standards. So in each such place you have many atomic clocks. By the way, in Israel there is also a National Laboratory of Standards. It's a small place, so with about half a person, and several atomic clocks. So they measure different standards. So that exists. So actually, Israel, for example, is a part of the world time standard, but it sits on about 20th place, I think, and it's really non-linear. So. I think that the measurement that comes from Israel is taken with some very small percentage inside the the measurement that is after that defines the central the time, the uniform time of the world. So write it down. Ilan and Eberly. It's called optical resonance. And two-level atom. So it's that's the name of this book. So it's a well-known book. It's a small one. You can find it in many places. Most probably can be found on the internet as well. So now we want to add decay to the story. So it's done phenomenologically. So it's not rigorous, of course. So it's not what we can do, but we just add, as we said, we have this time development of a density matrix, which goes like the Hamiltonian. So, and the
commutation relation between the Hamiltonian and density matrix. And here, so this is what we did until now. So now we add to this story is the time decay of the density matrix. So this is really a decay process, okay? So it's something that causes decoherence and decay of the story. So, and there are two different types of decays that can be immediately recognized, essentially, based on the language that we developed during the discussion of block sphere. So you see that block vector consists of two essential parts. The one part is the population, is W. It's the difference between the population of the excited state and the ground state. And the second part is this UV plane, which is the plane where we see the development of the optical dipole. So now this optical dipole can decay differently as compared to the population. So essentially there are two different types of decay that can be considered. And this is the well-known nuclear magnetic resonance NMR language of this story. It's NMR language, okay, so there are two types of decay. So the first one is the population inversion, the population decay, or population inversion decay, population decay. So this is also called as T1 time. Or in the NMR language, it's called like a longitudinal relaxation. So NMR language is probably here. Longitudinal relaxation. So it's more in spectroscopy. It's more known like T1 time, and NMR uses this name of longitudinal relaxation. So, but only the additional process that can be done is actually the decay of this off-diagonal density matrix element. So population decay is the decay of on-diagonal elements of the density matrix. On-diagonal elements. On-diagonal elements. So nothing more to follow. Okay, so anyway, so it's on-diagonal elements that decay of the density matrix. On-diagonal elements of the density matrix. That's the first mechanism. The second mechanism, which is not necessarily the same, so they can be decoupled. It's the off-diagonal element decay, or coherence decay. Coherence decay. This is essentially why, in the first place, the density matrix was invented for. Right? So the coherence decay, or it is known like a T2 time. Okay, so this T2 time in the language of NMR is the transverse relaxation. And it is related to off-diagonal elements. Of the density matrix. Okay, so that's two different types. So they can be related. They can be independent. So we will try to give some interpretation to that, but first we will probably write down the Bloch equation by using the introduction of these two different types of decay. So essentially we have this W, the time derivative of population inversion. So the time derivative of the population inversion should be written like radio frequency multiplied by V. So that was the initial type of the story. And now we get this additional term which describes the time decay of the population of W. So essentially I can stop here, right? But now we want to get some equilibrium of the population. So and therefore we add here the 1/2 of the equilibrium of the population. So if the equilibrium, so usually the equilibrium of population from our point of view is, that the equilibrium population is just the -1, where the population goes down to the ground state. It can be different value, so it can be different value depending on the problem that you solve. So that's T1 time. So the population decays with the T1 time. Okay. So now we have the equation for U. The derivative in time of U is equal to the part that we know is delta multiplied by V. And now we get 1 over T2 time multiplied by U. So U decays with the rate defined by the T2 time. And now V, derivative with time, also decays with the same, but we have minus delta multiplied by U minus omega radi multiplied by W. That's the part that we had before. And now we add the decay of time C2 of this off-diagonal matrix element. Right? So these are now the optical Bloch equations with time decay of two parts, right? So we have T1 time and we have T2 time. T2 time defines the decay of off-diagonal elements, and T1 time defines the decay of populations. Okay? So now we need to solve that. The solution is much more complex. So they are significantly complex in this situation. So actually, it exists. This solution, sort of analytical. So it's called story solution. I don't write. So if you want, you can look in this book, the Ilan and Eberly. So it's a complex solution. But you can do it numerically. But before discussing that, at the end, I want to essentially to consider more or less a single type of decay, which will be the spontaneous emission. But now at this point, I want to discuss several possible decay mechanisms. Okay, so and give some interpretation to this decay times T1 and T2. Right. So. Right. Now, let's consider essentially this, interpretation. So, interpretation of T1 and T2. So we consider the density operator. So the density operator now is this sigma. The operator now it's the sum over n with the probability Pn to find our ensemble in a certain state. So that's now, you know, our story complicates because we include into consideration different members of the ensemble. So it's not a single atom anymore. So there are many atoms that plays. You know, that's usually what you have. So you have a lot of atoms to interact with, and many atoms to interact with. You have to actually sum different probabilities to find your ensemble member at a certain state. And so this is how your density operator should look like in this situation. Right, so the Pn is the probability of a certain ensemble member to be in this state, psi n, to find it in the psi n. Okay, the psi n, so this wave function of an ensemble member can be written, of course, as the sum over I c probability of I of an ensemble member n to find it. Right, so to develop, we can take the state of the member of the ensemble to develop it in certain basis. So that's the basis of vectors I. So then this projector operator of psi n. Psi n can write as a sum over ij ci of n cj of n star, so the complex conjugate of cj multiplied by I j, projection operator ij. Right? So that's the projection operator. So then the density matrix that we have to consider is sigma ij, the element of the density matrix, is sum over n Pn multiplied by Ci of the member of the ensemble n multiplied by Cj of the member of the ensemble, complex conjugate of that. That's the density matrix element. Right? So now this density matrix we can so these two numbers are complex numbers. We can explicitly write it as a modulus multiplied by the base. So it's a sum over n Pn multiplied by modulus of Ci of the n's ensemble member, modulus of Cj of the n's ensemble member, multiplied by to the e to the power of I, phi n minus phi j n. So explicitly write here the phase of each complex number that we have. Okay. So now we can consider two different elements that start from on-diagonal and off-diagonal elements. We know that they decay differently, so they can decay with T1 and T2 So let's start on-diagonal elements. Diagonal elements. On-diagonal elements 1. So on-diagonal elements, there's no 1. That's on-diagonal elements. 1 is on-diagonal element. So we have here sigma II, right? So sigma II, so this and this is essentially the same, right? So we have sigma II equal to sum over n Pn multiplied by modulus of Ci of the nth ensemble squared. And that's the matrix element. So now we need to add the decay mechanism. So decay mechanism goes like a 1 over T1, 1 over Tn. Let's call it gamma. So we'll call it gamma I for each ensemble for sigma I. So this T1 can be different for different populations. So, for different levels. So it depends on what level you consider, right? So this is why it's actually gamma I. So each level can have different type of different rate, not type, rate of decay. Okay, so now we can say that therefore sigma I of the ensemble member n as a function of time to decay will decay with the rate Ci n of 0 at 0 moment multiplied by e to the power of minus gamma I multiplied by t divided by 2. So we divided by 2 because we know that the matrix element, essentially as we wrote here, the matrix element decay with the time 1 over t or gamma. So if we square that, to get the density matrix, so the factor of 2 will be gamma. Okay, so we need this factor of 2 in order to describe that this is the amplitude that decays with the rate 1/2, which says that the density matrix element will decay with the rate gamma. Okay, that's therefore the decay of on-diagonal elements as a function of t will be just e to the power minus gamma I t sigma I at time 0. If there is no, right, so if there is no excitation anymore, so we just drop everything, so, and we consider what's going on with the matrix elements due to decay only. Therefore, this what should happen with the decay of the matrix element if we talk about on-diagonal matrix elements, so all populations. Okay, so now let's go to off-diagonal elements. So that's 2. So this is off-diagonal elements of the density matrix. So off-diagonal elements of the density matrix. So this is the sigma ij of t is equal to Ci modulus multiplied by modulus Cj, so of 0 at 0 time. At 0 time, Cj modulus at 0 time multiplied by e to the power of what we have here minus gamma I plus gamma j divided by 2 multiplied by t. That's the time decay to the t1 time, right? And now we have to sum over the elements of the ensemble Pn. That's the probability to find an ensemble member in certain state multiplied by e to the power of this guy, right? So minus, sorry, not minus I, without minus I multiplied by phi I, phi j, phi I n minus phi j n. That's the the phase difference between these two states, right? On which we use the projection operator. Okay, so now we can say the following. So we can call this phi I, phi j, right? So phi I of n minus phi j of n equal to omega I j t, the ensemble level of the ensemble member n. So and now we can say the following. So we can say that this essentially sum over Pn e to the power of I omega ij t of n over n. So this omegot can be different. So in sum over this story is actually can be approximated very well by the exponential decay beta ij multiplied by t. So this is due to the dephasing, or due to the accumulation of the dephasing of different oscillations. So here, each ensemble average, each n gives you a different frequency, right? So just sum over all these different frequencies. So summing over all different frequencies brings you finally at the decay of the contrast of the oscillation. Right? So and this can be described by exponential decay of this contrast. I will show you just a geometrical sort of geometrical representation of this in a moment. So just keep following me, even if you do not really follow that. So and then T2 I can describe like 1 over T2 will be equal to gamma I plus gamma j divided by 2 plus beta ij. So the decay mechanism, which is related to T2 time, right, can be real. First of all, it also relates to the decay due to the T1 time. So once you have a T2 time, so once the once T1 time, so the on-diagonal elements decay, so this will bring also to the decay of the decoherence. Sorry, decay of the off-diagonal elements. So this is sort of one-way ticket. If you start to decay your population, and the population decays, the dipole moment will decay as well. But in addition, it has an additional factor. So if this additional factor is much stronger than this guy, if you by some reason choose to work with some states that do not decay, then this guy do not follow, so do not play a role. So we can forget about that. So population stays okay. But we have decay due to this term, the dephasing, and this term will decay the coherences only without touching the population. So the coherence will decay without touching the population, right? So that's the meaning of the T2 time. Okay. So in the language of two-level atom, right? So just to say some few concrete words about that. So what is the T1 time? Yes? Any? The population decay. So the decay of the population is defined by spontaneous emission. So spontaneous emission will decay the population. So the excited state will decay due to the spontaneous emission down to the ground state. That's T1 time. A T2 time is a different story here. So it doesn't exist in the presence of a single atom. So we need to take, so as you see here, we really have to sum over some different ensemble diverging. some different ensemble members. So this T2 time can be related to some sort of different decoherence mechanisms, and it can be of different type. Okay, so they can be collisions, for example. Now collisions can bring you to a decay of coherences only, and not the population decay. It's also some sort of distribution, or different distribution of something else. For example, velocities. So if you have a gas of atoms at certain temperature, then all atoms has some different velocities, right? So they distribute over the velocities due to the temperature. So the Maxwell-Boltzmann distribution of velocities means that you have many different probabilities to find your atom with different velocities. So different velocities give you different Doppler shift to interact with the laser. So, and this different Doppler shift will realize this decay. So these differences in the phase of different frequencies for each ensemble member, and therefore you should somehow take into account this ensemble averaging, and you will see that the coherences disappear. So the coherences goes away, while the population does not. So the population can stay untouched, but coherences decay. So on-diagonal elements of the density matrix stays the same. Off-diagonal elements can decay to zero. That's exactly where the four or strengths of the description of your problem with the density matrix comes into play. So you can describe two different mechanisms of the decay, one for on-diagonal elements, one for off-diagonal elements. But that's true that once you have decay of on-diagonal elements, that will kill everything, including off-diagonal elements. Right? It's a killer mechanism. But it's not necessarily the only one mechanism that can kill the coherences. So coherences are more fragile. So they are more fragile and then can be killed by a different type of so, by the way, collisions can be of different types. Okay, so for example, so if we talk about different types of so if you talk about different types of collisions, or different types of decay mechanisms, so I should say that decay mechanism, T1 time, for example, for two-level atom, right? This is what we said. T1 time for two-level atoms is spontaneous emission. Spontaneous emission. And T2 time can be derived from, for example, collisions. However, T1 time can also be derived from collisions. Can be also collisions. And this has two different types of collisions. So this one is inelastic collisions. So these inelastic collisions change the population. So they can change, can take the atom from one level to another level. You have inelastic collisions. There are elastic collisions. Here, for example, this is the elastic collisions. Elastic collisions do not affect the populations. So it cannot redistribute the population of the atom between different energy levels. But it certainly can affect the phase with which it interacts with light. And then this type of collisions will cause the decay of the type T2. Okay, so the T2 essentially can be also divided in subclasses. Okay, so this one is a subclass. So essentially 1 over T2 can be written like a 1 over T2 prime plus 1 over T2 star. It's not very important how to define them. But T2 star here is the inhomogeneous effect. So inhomogeneous effect means that you have different values for different ensemble members. And this is, for example, the Doppler effect. Okay, so and T2 prime, they are homogeneous effects. Whose effect? So and that's, for example, collisions. Okay. That's a homogeneous effect, and T2 is inhomogeneous. So it can be either homogeneous or inhomogeneous. So, right, making all these nice specifications of the effect. So let's probably discuss a little bit some different types of them and what it can be affect by. So essentially, they're not the same. Okay, so they're not the same character. This is why we define different classes of this effect. So, for example, this effect. So, for example, this effect, T1 effect, is an irreversible effect. So, T1, once you decay the population, so the population gone, nothing you can do about that. So, you can only make the reverse, so you can start your interaction from the beginning. So that would not, you cannot play the games in trying to reverse this effect. This is the irreversible effect. Homogeneous effects like collisions are also irreversible effects. So they cannot be reversed somehow. You cannot engineer that. But inhomogeneous effects, they are reversible. So they are not truly harmful. So they can decay your orthogonal elements, of course. So that's T2 times. So if you write your equations, so you can see that this effect present. So due to, for example, Doppler effect, so you have different frequencies, so you sum over your ensemble, so you get the decay of your off-diagonal elements. But this decay can be reversed. So there is a certain interesting technique that shows that this is reversed. So essentially, this is a part of your homework. So at least to see how this Doppler effect kills the queries. So we'll see that everything is defined very well in homework, what to do in order to see how this queries disappear due to the Doppler effect. Okay. So you just take your, you take several atoms. So instead of taking only one, so you take several atoms. You make the average, and you see how the contrast of some fringes, Ramsey fringes, decay. So that's the simple story, right? So this is just to see how it kills the query. So the less simple story is not a part of your homework, though once it was. So it's actually a technique that is known like a Photon Echo technique. So this Photon Echo technique allows you actually to reverse this inhomogeneous effect, so reverse the decay of the queries of the off-diagonal elements and get the queries back. So in order to understand that, I can explain you, like on the language of the block sphere, this technique. So I'm not asking you to do that. It's a bit more work. So I leave you in peace without requiring that. So if you wish, you can realize that. So once you understand how it works, try to do that. So it's a photon echo effect, so it works like that. So imagine now the case that we have several atoms. And so all these several atoms, we essentially try to talk to them. And talking to them means that we actually apply on the Bloch sphere, we apply driving force, which is still on the direction of u as it was before. So we apply it like that. So now our Bloch reactor that fills the first starts to oscillate. So but now the point is that one atom, due to Doppler effect, right, the Doppler distribution of velocity, feels different frequencies or feels different detunings, right? So one atom will be excited by the first pi over 2 pulse, for example, in Ramsey mechanism, will be excited into the UV plane because it sees zero detuning. So it will be here. But the other atom will miss this point because it has a different detuning, right? Because the different velocity, it sees different frequency of the laser. So this different frequency of the laser says that the detuning is different, so it will be excited a little bit off of the UV plane, right? So, and another atom can be a bit below, right? So it's really depend on what the tuning is. So there are distribution of the tuning. So all the atoms will not be on the same position in the UV plane. I mean, they will be differently distributed actually along the axis, so somewhere distributed like that. Okay, so smeared instead of the clear position in the UV plane, they will be distributed around. And now we leave it to develop in time. So development in time, if you are exactly in the UV plane, you stay at the same place. Right? So nothing happens. If you are with the detuning, negative detunings, those that have negative detuning starts to move in one direction, those that are in the positive detuning starts to move in the opposite direction. And each of them moves with a different frequency because different detuning means in this matrix that we wrote before, it's a rotation matrix which depends on the detuning, right? It's developed in time. So one atom rotates very fast, another one rotates slowly, the other one rotates in the opposite direction slowly. So you can imagine that all these Bloch vectors will be distributed quite uniformly around the UV plane, right? So in the UV plane, after some time, you will see the distribution of these Bloch vectors uniformly distributed around that. That's the key of the coherence. So now if you try to apply the second pi over 2 pulse, part of atoms will go up, part of atoms will go down, part of them will be some will make the projection, partial projection up, partial projection down. You will have 50-50%. 50% up, 50% down. Whatever the time you wait, you will get exactly the same result. Right? So you wait some time, you wait more time, it's 50-50, more than 50-50, more than 50-50. That's exactly the decoherence time. So your off-diagonal elements decay to zero. Once you filled this UV plane totally, uniformly distributed your different vectors over the UV plane, you kill the coherence. That's clear, right? So now, this is an interesting point. This is not a non-reversible effect. You still can reverse that and gain back your coherence. How to do that? This is nice trick. So essentially, at a certain time, after you wait some time, and after waiting some time, you apply pi pulse. So what does this mean, applying the pi pulse? So let's look for different ensemble members. So let's look for a simple one that has detuning equal to 0. So the one that had detuning equal to 0 after the first pi over 2 pulse, it was excited into the UV plane, and it stays there, right? Now, it stays there and wait until something happening. And now arrives the pi over the pi pulse. So pi pulse takes, rotate you a half of the sphere. Rotating of the half of the sphere means that your vector will be projected to that direction. It goes through up and there. Okay, so it's now in this direction, pointing. Okay, fine. And then it stays and waits here in this direction. Now, what happens with a different guy? So let's see, it was rotated in this direction after the first pi over 2 pi. Right? So it's rotating in this direction. At a certain point, pi pulse arrives, and it's actually project this guy into this direction. Right? So what happens now? It continues to run in this direction. Instead of running in this direction, after the pi over 2, after the pi pulse that projected in this direction, it starts to run in this direction. So let's consider another guy that goes in the opposite direction. So this guy, after the first pi over 2 pulse, goes here, and pi pulse will project it in this direction, and it will continue its run in this direction. You see what's happening? So those that were running in the opposite direction, after this pi pulse, boop, they rotate and then start to run in the opposite direction. Okay. So and this happens with everybody. So the one that was very fast, and it arrives further. It was very fast. It arrives further. The pi over 2 pulse rotates in this direction, so it's still very fast. It goes back. The one that was slow and runs very little, so it rotates by the pi pulse and runs very slow, then it runs in the opposite direction. So they were all distributed in this part, right, of the sphere after a certain time. Now you project them all on this direction and wait exactly the same time as you waited between the first pi over 2 pulse to the pi pulse. So they will run back, and arrive in the same at the same position. So they will be back to be coherent. So they will regain the same direction, right? So they distribute. It's so in the first time development between the first pi over 2 pulse until the pi pulse, they smeared over all sphere, all UV plane. But after the pi pulse, right? So those that were first, you suddenly project to be in the tail of the distribution. So and they start to run back, and so they actually regain the coherence and arrive at a certain point, which is exactly the same time. They regain the coherence. So that's the sequence is pi over 2 to make the coherent superposition, then it's pi pulse, and then it's pi over 2 pulse here after the same time. That's time t, that's time again t. And after this, and this again pi over 2 pulse. So all we had added here in this story is this pi pulse. So this is called the photon echo. Photon echo. It's something that very nice. You can, if you, that's the picture also from this book, by the way. You can see it in this book. So this is a picture of runners. So the runners, imagine that you have different, starting point and this different ways that you have the runners on the stadium. So this runner starts at certain point. You make a start to them. Give initial time, so everybody starts to run, and all of them run at different velocities. Right. So at a certain point, they are distributed all over the stadium, right? Because everyone runs at different frequencies, so at different velocities, so they start to be distributed all over this stadium. Then you make at a certain point, you make another sign, so you say revert. Right? So now starts to run back. So everybody reverts. Right? So instead of running in the same direction, everybody arrives at some position and reverts. It starts to run in the opposite direction. Those that were running very fast, they arrive at the largest distance, right? So, but they still run very fast. So it will take exactly the same time to them to reach the starting point. And so everybody reverts their direction, and after the same time, they will actually reach the initial point. Okay, that's the idea. It's a very simple and elegant idea that actually tells you how this coherence can be regained back. So it's not a part of the homework, so it's just to tell you the principle. It works. It's very useful technique in spectroscopy, so people continue to use that. It's really some part of this T2 time can be really reversed, can be really regained. The coherence can be really regained if you use this Photon Echo technique. I wanted to tell you about that, so just for you to know. You will see only the first part, how this effect actually kills the coherence in the homework. That you wouldn't see how to revert them, but you know how to do that. So you only need to add a certain pi pass in your story in the needle between the pi/2 passes, and then you should be able to gain the coherence in the story. So let's end up for today. So then next time. This will be the last lecture, so I will discuss the last lecture this back to a single atom picture. So we'll take the spontaneous emission and we will see how the spontaneous emission. So we will see actually something which is related to a steady state solution of optical Bloch equations. This will be the main subject of the last lecture, so the steady state of the optical Bloch equations and what we can learn from this steady state solution. Okay, so